Welcome to the second in a series of introductory videos for the iMachining for NX CAM software. In this video, I'm going to cover 2D iMachining. In the previous video, we saw how to set up the iMachining databases for your machine and your material. Now we're going to see how that applies to the actual toolpath. So I've actually created all the different types of toolpaths for iMachining 2D, and we're going to go through them real quick in this video. So let me just show you how you create a brand new one. So we'll go create, choose from the type iMachining, and between these two icons, we're going to do 2D iMachining, which is essentially just a optimized pocketing toolpath using the iMachining toolpath. Everything on here is the same, so we'll just say the 1-inch tool, and we'll go into the main dialog. Now, as a user-defined operation, there's not much information here. It's going to be in the user parameters where you actually see all the iMachining data. Okay. Now, let's say, for instance, we wanted to do a roughing path. So technology is iRough. We can always just confirm our settings here like we did in video 1. We'll select our geometry. So let's say we're just going to do this top pocket. Just grab that there. I have my tangent curves turned on, so it found the rest of that for me. Okay, go down to cut levels. So the geometry tells the toolpath where it's going to travel in X and Y. The cut levels will tell it where to travel in Z. Okay, and we'll just choose our levels. So I'll just say upper level there, lower level down to that guy. Cut parameters is essentially what happens inside the toolpath. So as a roughing toolpath, we want to leave some material behind and the walls and the floor. So that's what we've done here. Cutting direction will be climb. Cutting angles is how the iMachining toolpath controls the material engagement. So you can see here cutting angle min and max. Those are going to regulate as it goes through the toolpath, again, to maintain that chip load. So the basis of iMachining. Morphing Spiral, as we'll see with some of the toolpaths, is what happens inside the toolpath itself. So to do this pocket, it'll find the mathematical geometric center. It'll morph out from there in a spiral, and as it gets closer to the walls, it'll morph the spiral to match the contour of the actual geometry that we selected. And the efficiency of that spiral, how many times it has different initiation sites throughout the geometry, all of that is pretty much controlled in the efficiency and the entry rate. If during the toolpath there isn't an ability to do a spiral, let's say we had a spiral here, and now we needed to find a way to do this kind of bottleneck right here, then we would start machining channels. So this is an automatic inside the toolpath, and to control the efficiency of that channel, the different parameters of that channel are found here. To remove any kind of channeling and morphing spiral combination, we can turn off the online moding, and it'll just try and do a spiral completely over the part. iFinish and iRest, we'll see once we get to the iFinish and iRest portions of the toolpath. And then more, it's just simply controlling the arcs inside the toolpath itself. This is a tricoidal toolpath. There's many arc movements. Non-cutting moves is essentially just the helical entry. How we're going to enter into this pocket. Helical entry by default. You can control the ramping angle. If you had a non-sensor cutting tool, just uncheck this box, and then you can control the step down of that entry helix as well. And then additional parameters to control the in-pocket positioning. If you had added a drilling operation as part of your operations list, and you wanted to use that hole as a pilot hole for this iMachining operation, then you could find it in this list, select it, and incorporate it into the calculation of the iMachining toolpath. Okay. Scroll down to the bottom here. I showed in video 1 that the wizard has the material information of the tool and the helical angle of the flute. Both those go into the calculation of iMachining to how aggressive we can take the toolpath. But an additional level of calculation is found in the wizard data. Go into wizard data. You can see we have machining level, which is a level of aggressiveness of this calculation. Right now it's set to level 3. And that gives us a feed and speed of 64 inches per minute and a RPM of 4,600 RPM. Now, that is at level 3. That is an automatic calculation. Those feeds and speeds are calculated for us by iMachining. But let's say we wanted to go a little more aggressive with this toolpath. We can rev this up to level 8, and you'll see now that the feed and speed have increased considerably. So machining level is simply just the level of aggressiveness of this calculation. The step down and step over, again, are also controlled by iMachining. You can see them down here. The step over are such, and those are also controlled by the machining level. So we'll see that those get very aggressive as we change that as well. The step down is controlled by the cutting length of the tool. So in my tool definition, I told the software that I have 1.5 inch cutting length. But this pocket that I've defined is only 0.865 in depth. So we're taking it at full depth of cut. So we're doing one pass of 0.865 inches down, and that generates an ACP of 0.55. The ACP is actual cutting points along that flute that are in contact with the material. It's a way of calculating the efficiency of this tool path. So if we have 1.5 inch cutting length, but we're only using it for 0.865, then we're really only doing 0.55 or 55% of efficiency. If you don't like this number, let's say this is a very strong material and this is too aggressive of a cut, you can reduce all that by going to user define, and you can define the number of steps or the step down. So let's say we wanted to take this in 2 steps. If I set it to 2 and then click apply, it recalculates, so it has 2 steps, 0.43 of a step down, and now the ACP is only 27%. So we're actually reducing the efficiency. But if there's a purpose to this number of steps or the step down, then we set it here and we make it part of our calculation. Now I'm actually not going to calculate this toolpath because I did previously. So let me just hit cancel, and we'll take a look at the toolpath as it would have been calculated. So as you can see, we've got a little bit of morphing spiral going on here with the entry helix morphing out, some bottlenecks, and some inability to do the morphing spiral here. So it comes out to be a separation channel. All you're seeing here is the separation channel movement. As it gets closer to a corner, you can see that it's actually working its way into that corner as well. So that is the third aspect of iMachining, what we call the D-slot tricoidal. A lot of this is to maintain material engagement, but maintaining the chip load at the same time. So we're not overworking the tool, we're extending the tool's life. At the same time, this tricoidal toolpath, the iMachining toolpath, reduces the cycle time. So it is a very optimized toolpath, as you can see here. Now, I showed you in the toolpath that there is different technologies. Let me just get back to the toolpath. There is iRough, iFinish, iRest, and iRough plus iFinish. So I have all those represented here. So we'll go through each one very quickly. Let me just get, again, out of this toolpath. So this was an example of iRough. I left 10 thou on the walls and the floor. I used a 1-inch end mill to machine down that bottom floor. If I wanted to machine these side pockets, well, one edge of that pocket is actually open, and we have the ability to do that. I set the geometry as all those edges along that pocket, but I told it that the back wall is a wall, not to cross those lines. The front edges are open, telling the software that the tool can actually cross those lines. So this is actually the same toolpath, just copied and applied to just that edge right there, that platform. So you can see it does a little bit of a D-slot tricoidal, a little bit of a separation channel kind of action going on there to make sure that it can machine that pocket. And we do that by setting it as an open edge. So let me just open that up real quick. Okay, and we'll go to our geometry. And I set edges 6 to 9 as open. So the red indicates that it's open. I'm telling SolidCAM that it can go across those lines and machine that option there. Now, the other technology called iRest, I'm using a 1/2 inch end mill. The iRest is a similar toolpath. I've just told it I'm using a smaller diameter tool, and it focuses on what was remaining from the 1-inch operation. So if we open that up real quick, I set it to iRest, and then when I get to my cutting parameters, I go to the iRest tab. I told it to look at what was machined by the very first operation using that 1-inch end mill. It was a 1-inch tool diameter. I left 10 thou on the walls and the floor. I'm now using a 1/2 inch end mill. So iMachining calculated that the 1-inch could not do these corners. So it actually just focused just on those corners. So the purpose of iRest is simply just to step down the size of the tool to whatever size you want, and then allow that new tool to do what the first tool could not do. Now we have an example of iFinish. So essentially, I'm using that same 1/2 inch end mill. I told it to finish the floor using iMachining. The walls and the floor are now done by this iMachining toolpath. Let's open this up real quick. Okay, so it's set to iFinish. If we look at our cutting parameters, In the finishing tab, I told it to finish the floor using a contour style, but the options are contour or iMachining. Contour actually gives us that racetrack style look, so it actually has a better finish. But you could use iMachining as well if you were looking for that. In addition to that, we have additional finishing parameters for the walls, as you can see down here. So you can do a spring pass, you can add compensation to this operation. All of that results in a toolpath such as this. So you have that contour style toolpath. You can see that it's pretty much offset. If we zoom in on the walls, we can see that there's still a little bit of iMachining action going on. Just zoom out. Turn that toolpath back on. There's still a little bit of D/Tri-Coatal going on in that corner. Again, because the previous toolpath left behind 10 thou of material, so there's probably some additional material in there that's a little more than 10 thou. So the iFinish went in there and pretty much did almost like a iRest operation to finish that. So now that floor is completely finished. There is a fourth type of 2D iMachining, and that is the iRough plus iFinish. So as we saw before, I had a iRough operation and an iFinish operation. And what I did there was I did roughing with one tool, so let's say tool 1. Finishing was done with tool 3, 2 different tools. But let's say, for instance, this part, there was no need to change tools. I can do all the roughing and finishing in one toolpath using iRough plus iFinish. And what we get from there is in the cutting parameters, we get the option of iFinish as well as all the roughing options. And as we see, the result of that is an overlapping of the toolpath. We're doing some iRoughing as we enter in, we rough that out, and then if you really look at it, we're doing a finishing as well. You can see a little bit of that contour toolpath overlapped with the iRough. So the purpose of iMachining is the reduction of cycle time, the increase of tool life, and optimizing the toolpath as it goes along. And as you can see, it simply works off of the geometry provided by MX. Any questions on this? You can always call us at our main tech line. Let's stay tuned for the video 3, where we talk about 3D iMachining. Thanks for watching.